Yes.
Am I audible to you? Yeah.
Yes. Sir.
So in the last lecture, we did some flux calculation for various scenario, and today we are going to understand the EMF as per the Faraday's law. So as per the Faraday's law, the EMF induced we can write as minus d phi b by dt. So at what rate the flux is changing. So we'll take some simplest scenario and we'll see that how the flux rate of change of flux can give us the induced EMF. So so this is the field which is confined within a boundary, as you can see, and let's call the uniform field. We can assume its value to be B. And what we have is a connecting loop. So we have a connecting loop in a shape of a square and having dimension A. And the region which we have represented here, let's say this is 3A. So I'll try to make this a bigger slide. One. And some agent, some external agent is pushing this loop through this region, and it is trying to maintain the velocity. That's called V. So in a way, we can say that the loop is moving with constant velocity in and passing through this particular region. Taking the inward flux as negative and outward flux as positive, we are supposed to plot the graph between the induced EMF and the time. What we can realize that as the loop will enter, the flux will start through the loop, and it will be in the growing phase till it completely enters the mid, this region, right? So flux through the loop will be in the growing phase till it completely gets inside the region. And for a while, the flux will remain constant because you have arrived at the maximum value. So no more change you can expect. And then when you start leaving the region, the flux will be in the decreasing phase, and therefore it will be a time varying flux, and again EMF will be induced. So while entering the medium or the region, because the inward flux will be growing phase, so as per the Lenz's law, the induced current in the loop will be in which direction? So as the inward flux will grow, the current will try to compensate, right?
Yes, sir. Sir, and clockwise.
The flux is inward into the plane. You're trying to compensate. So you're trying to enter the region, right? So your inward flux is increasing.
Yes, sir.
So how to manage it? How to minimize it or compensate? How the current should create its own flux?
Okay. Sir, anti-clockwise, because outward flux has to be created.
Correct. So because the flux that the loop is generating is outward, so we can say the induced EMF for such flux we will take as positive. Okay.
Yes, sir.
So anti-clockwise current will establish, and in such case we have to represent the induced EMF as positive value. Now, given the dimension, velocity, and B, can we calculate the d phi by dt?
Yes, sir.
So after some time t, we can draw something like this. So let's say the loop has entered X value inside. What is the flux count? The first step is just find the flux, and it is pretty easy to find. How much?
Yes. Yes.
Dx, and therefore differentiation is also easy. So we can say d phi b by dt, because everything else is constant. So the dx or dt is nothing but the velocity of the loop, isn't it?
Yes, sir.
So we can say the modulus of induced EMF is going to be BAV. We only take the value and we decide the sign on our own. So you can clearly see the EMF induced is a constant quantity. It is not a variable quantity. It is BAV. So it's a constant value. And this will occur only for the time the flux is changing, and this will stop after what time? A by V, because after A by V, it will be completely inside, isn't it?
Yes, sir.
So when you are completely inside, the flux will be there, but the change won't be there. The flux will not change with time. It is only flux, right?
Yes, sir.
And because the flux will not change, so till the time the loop will arrive at this end, till you arrive at this end, after traveling how much? So how much time it will take to reach here? It is 3A by V.
Yes, sir.
So till 3A by V, you won't see any induced EMF. But the moment you try to exit this location, the flux will be in the decreasing phase. And you can see that the flux if I call this as X, this will be A minus X. So flux here will be BA or BV into A minus X, right? How much is flux?
Yes, sir.
It
So
is
BBA minus X.
BA
BA minus X.
A minus X.
Yes, sir.
And therefore, if you differentiate, the BA is constant, we will get minus V. Which simply means the
Induced
flux,
flux.
yeah, the flux change is negative, so the EMF induced will be minus d phi by dt.
Yes, sir. DA.
And in this case, you can say E induced equals to minus BAV. Okay. So it is confusing here because the sign is the EMF induced is a positive quantity, but we need to also understand that the inward flux itself is negative. So if I write the inward flux as a negative value, the answer will be change the sign, isn't it? I have taken the inward flux as positive, so we are getting the reverse order sign, right? So the
Yes.
moment you take the inward flux as negative, so see, we started with the positive value flux, right? Although we should have written here negative, right? Because we are taking the inward flux as negative. So taking inward flux As negative, the E induced will have the proper sign. So this will become BAV, and this will become minus BAV, isn't it? So we started with the assumption that inward flux is positive, so we got these signs. But if I start with the sign of flux, and if we call the inward as negative, then automatically the induced EMF will have the proper sign. It will tell you that what is happening. Okay. So a negative induced EMF is representing that the current will be clockwise. Is this clear?
Yes, sir.
And again, once you're out of the loop, the EMF induced will not be there because there is no flux at all. So this is BAV positive and this is BAV negative. And this is the graph of the EMF versus time. I hope this is clear.
Yes.
And you can also clearly see that for some interval there is no EMF induced. So I can draw by the red line at the t-axis, which means it's zero value. Okay. Similarly, we can also demonstrate another situation, which is again very common. Taking inward flux as negative, we can easily derive the relation. So let's say we have a situation slightly different from the previous. Here we have the magnetic field, which is on the one side of the region, or there is a boundary. On one other side of the boundary, there is no field. And we have a semicircular loop which can rotate about its center. So we have semicircular loop. I'll remove the half of the portion. Okay. And now this loop is rotating clockwise, let's say, with constant angular velocity omega. Okay. So the angular velocity is constant, as you can see. And if I choose this instant as t equals to 0, then we are supposed to plot the graph of E versus time. So can you guess the graph? How it will look like?
Sir, I'm getting it to be a constant graph.
Yeah, that's correct.
Okay. So, are you speaking something?
No, no, no. So you got the answer, no?
Oh,
So what is
sir,
the EMF induced part?
sir, B R square omega by 2.
Excellent. So the E induced part is B omega R square by 2. But it will remain constant. So again, it's a similar thing. Here, it will first at some random instant. I'll just show you two instant. So just a moment.
So,
Yeah.
sir, I guess last class you had sent a screenshot of mains IIEEE.
Okay.
That archive, one of the pages screenshot you sent, sir.
Yeah.
Sir, in that, let me just tell which question number is it. Sir, the 12th question, is it like about this?
Let me see. I don't remember. Let me see. Last lecture.
So last to last.
Yeah, yeah. Yeah. That is question number two. Question number two, right?
Oh, question 2, sir.
That is from here. Yeah, I think so.
Sir, neutral inductance.
No, that will come at the end of the chapter. Don't worry.
Okay, sir.
I mean, we have to study a lot of things. I mean, this is the beginning only.
Sir, the
So-
12th question at the end in section B.
Just a moment. Yeah, it is similar to this. After this, you have to find the power. So again, this is a part that we will study in detail. That's easy only, but we will study.
Yes, sir.
Like you can solve question number 23. It's the bottom.
Oh, yes, sir.
Just have to differentiate and write minus d5 by dt. That's it.
Yes, sir.
So the E induced is now you can see that there is no time. You won't get any instant when it is either increasing or decreasing, right? Can we have the motion some cooling off period like some interval for which there is no change? Is it possible here?
Uh,
Is it possible to have an interval without any change?
No, sir.
No, this is not possible in this case.
Yes.
So here the graph will be like this: constant, then change of direction, again constant, then change of direction, or you can say sign polarity, then constant, then again. And it will continue like this. So for every pi by omega interval, so we can define the pi by omega, 2 pi by omega, 3 pi by omega, and so on. Okay, like this. I hope this is clear.
Yes, sir.
Just for the sake of record, I'll just put the derivation. So flux will be here half r square theta into magnetic field. So only this part will have the flux, right? And the area of a sector is half r square theta into b, and therefore the d phi by dt becomes, I'm just writing the value, b omega r square. Or basically I can say b r square by 2 into d theta by dt. And as you can see, theta is growing in value. So d theta by dt is a positive value, so you can add omega by 2. I hope this is clear.
Yes, sir.
Uh, so imagine a situation in which we have a circular region with magnetic field. anyway. So we have we have to believe that it's uniform magnetic field confined in a circular region of radius r, and we have a square loop whose side is equal to diameter of the circle, like this. And it is moving with velocity v. So now I need to mention the dimension. Can you find the EMF induced in this loop as a function of time t?
Yes.
This is t equals to 0. So find E induced as a function of time t. Try this.
Yes. Sir, can you just come back in a minute?
Yeah, sure. So you understood how to do this?
Sir,
So
yes, sir.
you can draw another diagram at some instant like this. Okay.
Sir, sir,
Yeah.
sir,
Am I audible?
yes, sir.
Yes.
Sir, I related. I mean, like, if it has gone like, sir, if we draw a line from the center to the end of the circumference, yes, sir.
Then you are supposed to find this area, right?
Yes, sir.
So from the sector area, subtract the area of triangle, you will get the answer.
Yes, sir.
And to find the sector area, we can do this because this distance we know is VT. In time t, we will travel VT, right? So this is R minus VT, correct? This is R.
Yes.
Calling this as theta. So we can write the answer as,
Sir, I got the answer in terms of theta.
yeah, that's fine. And we can substitute theta later on. So the area we can write as half R square 2 theta, right? Minus half into base, which is base is how much? 2 R sin theta.
Yes.
Half into base into height. And height is how much?
R cos theta. Oh,
Yeah,
yes.
let's write out. That's fine. That's fine. R cos theta, not an issue. So if I write the flux, the B will come. So let's find the dA by dt. Because at the end of the day, it's the flux is BA. So d phi by dt is like B constant. So it is dA by dt itself, right? So we can pretty much divide the area. So dA by dt becomes R square d theta by dt minus R square. And it is basically sine theta cos theta is, we can write sine 2 theta. So d by dt of sine 2 theta, right? We can write like this.
Yes.
So r square d theta by dt minus r square by 2, and this will become 2 cos 2 theta into d theta by dt, the chain rule. So the dA by dt turns out to be r square d theta by dt, we can take common. So what we are going to get is 1 minus cos 2 theta. And to find the d theta by dt, we need to relate the theta in terms of other quantities. We can add cos theta equals to r minus vt upon r, which you can add as 1 minus vt by r. And if I differentiate both sides with respect to theta, I mean time, you can get minus sine theta d theta by dt equals to 0 minus v by r. Am I right? So the d theta by dt turns out to be how much? V by r sine theta. Is this correct? So finally, dA by dt, how much you're getting? So r square and d theta by dt is V by r sin theta, and 1 minus cos theta we can write as 2 sin square theta. So the answer is very nice, simple answer. What is the answer? It is 2VR sin theta. Understood? Is this clear?
Yes, sir.
So the EMF induced will be B into dA by dt. And so the answer is 2BVR sin theta, and we are done. Okay.
Yes.
So what is this r sin theta? R sin theta is basically this length. This is r sin theta, isn't it? And this length we can find using the Pythagoras. R square minus, can be write like this? Yes or no? And therefore we can write as under root of. So we can write EMF induced equals to 2BV under root of A square minus B square, which is A plus B into A minus B, which will give you VT. And because we have some term in the square root, and for this to be defined, we can say this is only true when 2R is less than more than VT, right? So this is only true when T is. Of course, after that, the equation will change.
Yes.
When it is when VT exceed 2R, in that case, you have to write E induced equals to 2BV, and we have to make a small change here. That's it. Okay.
Yes.
So this is how we find the answer for both cases. Later on, we are going to see a very simple method to solve such question, which we can solve in one line. But because we are trying to achieve things through the flux definition and the definition of EMF induced as proposed by proposed by Faraday, so is the answer. So our answer is coming like this because of those assumptions or those formulas that we have already. Now a loop. So now we'll relate something called a relation between flux change and charge flow in the loop. So let me elaborate what I'm trying to say. Imagine we have a loop, or you can draw any random shape loop. So this is the random shape loop. So it will have some cross section. And the moment the current will establish, what will happen? The charge will start crossing this cross section, isn't it? So if I represent current like this, so if we do some arbitrary shaped loop, like this, and then charge is flowing. So as long as the flux will change, let's say there is a flux also associated with the loop. So we know that if this is representing the, let's say, I induced, so having the resistance of the loop as R, the I induced, or we can say the EMF induced, can write as IR, correct? So a loop with resistance R having induced EMF E, we can write this relation E equals to IR, isn't it?
Yes.
Now what does it mean is that the rate of change of magnetic flux is actually resistance into, this is the ohm, dq by dt. So as long as the flux is changing through the area of the loop, I mean loop means this area, I'm talking about this area, the loop area. So as long as the flux is changing through the area of the loop, current will be in the loop, and therefore a charge is crossing this cross section. So we would like to know how much charge has crossed for the duration when flux was in the constant change. Okay. So for the duration when the flux was in constant change, how much charge crossed a particular cross section of the loop? I'm saying cross section is here. So area of the loop is this, but cross section of the loop is only this one, the small part which I have shown there. So we would like to relate these two, and you can clearly see the answer is the dt gets cancelled. So you can say the flux in the loop is basically R into dq. And if we integrate, because we just want the values, we can say delta q equals to mod of delta phi. So the amount of charge that will cross the cross section of the loop for the duration when flux is changing through the loop is equals to the total change in flux upon the resistance of the loop. It is clear?
Yes.
Okay. So, okay, flux, what is the unit of flux? Oh, I never talked about unit of flux. So flux is basically BA, this is Tesla meter square. And the Tesla meter square is called Weber, WB. Tesla meter square. So flux is Tesla meter square, and you can convert, you can also get the dimension if you want. So there are various methods to get the dimension. We'll come to that. I hope this part is clear.
Yes.
So to find the dimension, you can use the Faraday law, which is the easiest way to get the dimension. So let me just do this part. Dimension of flux. So E induced equals to d phi by dt. And the dimension of any voltage is work upon charge. And this is, we want the dimension of flux. And this is the dimension of time t, as we can see. So the dimension of flux turns out to be work, time, and charge is current into time. So the time gets cancelled. So it is work upon ampere, the current. And work is force into displacement. So it is M LT minus 2, force into displacement. And this is ampere, which we cannot change. So the dimension of flux turns out to be M L square T minus 2 upon, not upon, you can say. So you can see that it is the energy. So one thing is clear that if I multiply flux with current, it must have a dimension of energy, right? So flux and current product gives us the dimension of energy. They have dimension of energy. phi into I. So phi into I will always have the, so magnetic flux into current is having the dimension same as dimension of energy. So just remember this small thing. So we'll do some problem based on the charge flow. Okay. So we have a square loop, and you can see it's a uniform magnetic field B, and we have a square loop. So now this loop is capable of transforming shape, let's say. And after this, it converts into a circle. Assume the entire structure is within the field itself. No need to worry, it's not going beyond the field. Dimension of the loop is L. Now, while the loop is getting transformed, so this is sometime 0, this is sometime t. So there is a duration associated with the transformation, because no transformation can take place without any time being spent. So some time must have elapsed before the transformation eventually acquired the final form, right? So we can say that when you're undergoing the transformation, the flux through such loop will be in the transformation phase, or you can say changing phase, isn't it? So for that tiny duration, it may be very small, but for that tiny duration, the loop will have some current, because the flux is in constant change, and some current will be established. And therefore, if I consider some cross section of the wire, some charge will flow through that cross section. So the question is, how much charge will flow? How much charge will flow during the transformation of loop? So this is the question. So you can attempt, then also.
Yes. So the resistance of the loop is to be, I mean,
Yeah, you can
is-
assume R. And because
So-
total length is conserved, so the resistance of the loop is also conserved. Because in the
yes, sir.
transformation, we are not changing the cross section area, right?
Yes, sir.
And neither we are changing the total length. So that is going to be same.
Okay. So,
Yeah.
so I'm getting BL square by R 4 by pi minus 1.
Very good. So it is BL square by R is the right answer. So similarly, we can say that if we have a and there is a device which measures the charge flow called the ballistic galvanometer. So there's something called ballistic galvanometer, which measures the charge flow in a loop. So it's a good advice. I mean, you can read about it if you are interested. In fact, even I haven't read a lot about it. But this is the device which measures the charge flow. And there must be some mechanism, but it's good to know about it.
Yes.
Okay. The purpose is to measure certain thing like you can say how much is the Earth magnetic field. Let's say I want to know in this formula the delta Q can be measured using the ballistic galvanometer, and this dimensional changes we can of course measure. So if we are at some unknown location of Earth and if I want to know the Earth magnetic field, I can use this trick to get the idea. So of course these things are for indirect measurement, but it is really powerful method to understand the strength of magnetic field at a location. So transformations are very easy. I'll show you some better way to get the same answer. So now imagine we have this infinitely long wire carrying current I, and there is a loop. So in the beginning, the loop was located like this, as you can see. Let's call the distance as A. Let's the loop size is also square loop. And now about one of its edges, the loop is flipped. So we are flipping by turning 180 degree, right? So in the due process, what will happen? The flux will change through the loop, yes or no?
Yes, sir.
So the question is how much charge will flow through the loop? I mean, charge means how much charge will flow through the cross section of the loop. So same question.
So,
Yes, tell me.
sir, mu naught I by 2 pi r ln 4 by 3.
So the flux will add or subtract. What you did?
Sir, we are calculating the change in flux.
The change will be like it is getting added or subtracted. Like what you're doing. So initially, see the changing flux is how much? So final flux and initial flux.
Oh,
So
sir,
we need to
3 by
understand
4,
something.
sir.
Yeah, we need to understand something like in the beginning when it is turning. Let's say imagine a situation when it is turning from this to the perpendicular situation like this. In this phase, the flux will decrease, right?
Yes, sir.
So it will be in the constant decreasing phase and this will become zero. And because the flux is in the decreasing phase, the direction of current will be, because the inward flux is in, the flux is always inward because the B is into the plane. And because the inward flux is in decreasing scenario, so current will flow clockwise, right?
Yes, sir.
Current will be like this: A to B, B to C, C to D, and D to A, right? In the next part, when you are here, so let's say A has come here and B is there, C is there, D is there. In the next part, when you go from here to here, the flux will further grow, right? And because the flux is in the growing phase, phase, so how the current will be there? Because the inward flux will grow, so you will try to create the outward flux. So current will be like this.
Yes, sir.
And what you can realize, the current earlier was A to B, and it is now also A to B only. In the loop, the current direction has not changed, isn't it?
Yes, sir.
So here the total fluxing will add up. So if I find the initial flux, which is certainly mu naught I by 2 pi ln2, and the final flux is how much?
Mu naught I by 2 pi ln 3 by 2.
So the total flux, the delta phi is basically phi1 plus phi2. It is not the difference.
Yes, sir.
The other way of thinking is if I take the initial flux into the plane, so once you flip it, it will become, because the area direction will reverse, right?
Yes, sir. So it will be the minus of that value.
So that will again add up. You can think
Yes, sir.
either way. So the trick part here is the flux gets added. It's not that we need to subtract, rather we need to add the value, and therefore the flux will be mu naught I by 2 pi, and then ln2 plus ln3 by 2 becomes ln3, right?
Yes, sir.
And therefore the total charge that will flow is reconnect as mu naught I by 2 pi r. Now this r is different. Uh, and see something I missed. A will come here, correct? A will be there.
Yes, sir.
So this is the answer. Okay.
Okay, sir.
Similarly, if we have a small region with uniform magnetic field, and if I put a conductor here, at a distance capital R away, and I'll take B, and the region in which the field is actually present, let's call it A, and the uniform field is B. This is a metallic conductor, or simply I say this is the conductor with resistance R ohm. Find the current through the conductor when B is switched off. If I switch off, how much flux I will lose?
Sir, oh,
Right now, how much flux we have?
sir, due to the B inside the conductor. But
Yeah,
not
only the
the-
area through which the flux
Yes.
is there is the up to A radius, right?
yes,
So the initial flux is how much? What is the initial flux? Tell me.
sir, B pi A square.
So the final will be how much?
And the B is switched off, so it's 0.
Excellent. So we can say that delta phi, the value wise, is B into pi square. And so the delta Q to the conductor will be
B pi square.
okay. So we need to know or understand the ability that whenever you do the switch on or switch off functioning of a field, the switch off will not, I mean, we cannot switch off something in 0 time. There is some time involved which we do not realize, because even we talk about the electrical circuit in which we have electron, the moment you switch off, the electron cannot apply brake on themselves because they have inertia. So
Yes,
it is for sure that even when we switch off, the electron will move at least few nanometer ahead before it will come to rest. Okay.
yes,
So some motion will take place. I mean, inertia will let you move. Even there is no applied field, we can assume some inertia will keep the current moving. And that current motion, due to the inertia, will keep some current intact. So of course, we can increase. There are some mechanism by which we can increase the inertia. In general circuit, this inertia is very small, so it dies out so fast that we think it's instantaneous. So to the level of human perception, it is instantaneous, but for machine, it is up to few or maybe hundreds of nanoseconds, which is certainly a big interval for them. So in the
yes,
chapter of inductor or inductance, you will actually, I mean, come to know about this inertia can be artificially sustained. So a circuit with high inductance are actually those circuits which can sustain the current flow even when the actual source is switched off. So that is how the property of inertia is continued there. Okay, so we'll study about the inertia of a circuit with high inductance. Technically, in normal circuit, the inductance is very small, and so the inertia. Okay, so we'll see that.
Okay, just come back in a minute.
Yeah.
Sir,
Yeah, yeah, I'm here. Okay, so now we can go to the next concept. So the most of the question in which we vary the area to get the flux change can be derived easily using the concept of motional EMF. So now we are going to study about motional EMF. You can add E motional. So motional EMF is the EMF induced in a conductor which is moving in some external magnetic field. Okay. So imagine again the same thing. Let's say we have some field. Imagine we have a conducting rod. I'm drawing a bit broader, but it's a thin rod. The length of this conductor, let's call it L. And the velocity given to this conductor is in the direction perpendicular to the length of the rod. So this is the direction in which the rod is moving. And for the time being, let's say the B is uniform. Or at least the B is in the location of a conductor, the value B is B, and it is normal to the plane, which means it is normal to the velocity also and normal to the length of rod also. Okay. So these are the things known to us. Okay. Now, every conductor will have free electrons. So if I consider a single free electron inside the conductor, and if we try to analyze the force, so first of all, as the conductor will go towards right, the electron by default will have no choice but to go right. So I can say the velocity of the electron is also right. Am I right? Understood?
Yes, sir.
So the electron is moving towards right. So you can understand this electron is moving towards right in an uniform magnetic field. So will it experience any force?
Sir, yes, sir.
So this will experience some force, right?
Yes, sir. Upwards.
Yeah. So V cross B will give you the force downward. Why? Because it's a negative charge, which we generally
Yes,
forget, right? So being a negative charge, the force will be downward. So the electron will try to go downward. So QVB, that's it. So the magnetic force will act downward, as you can understand, and therefore these electrons will start accumulating near the bottom. Now, as the electron will move from top to bottom, some deficiency will be developed here. And the deficiency we can depict as a positive charge collection. And because of the negative and positive charge polarization, an induced electric field will develop between the ends. And this induced field, which was not actually present, now will be present. And because the induced field direction is downward, the force on electron will be upward, because electron is negatively charged particle. Am I right?
yes,
So we can see that the electron will have the upward force, which is electric in nature, and a downward force, which is magnetic in nature. So as long as the magnetic force is dominating or dominant over the electric force, the electron will keep on coming down, isn't it?
yes, sir.
So the electron will keep on coming down. And if the electron will keep on coming down, then at the same time, we can say the electric field, the induced electric field will keep on getting stronger and stronger, right?
Yes, sir.
So a time will come when both will balance out each other, isn't it?
Yes, yes, sir.
And that is called the equilibrium state. So at equilibrium, what will happen? At equilibrium, both forces will balance out each other. and therefore we can say the E into E is equals to, now this is E only, EVB. E gets cancelled out. So what we get is the electric field that we got is, so because the V and B are mutually perpendicular, so we have the transverse value. So the velocity is right angle to the B, and this is the value of electric field. So what is EMF? So the EMF induces what? It is the potential across the rod, isn't it?
Yes.
So the potential across the rod is E into L, the field into length, isn't it? That's simple. And so we get the answer VB. So the actually what we derived earlier by flux change, the answer was same. If you remember, it was VBL.
Yes.
And now the emotional EMF is saying that the motional EMF, this we can call emotional also. And that is the proof that it is the moving part of the circuit which is capable of creating the induced EMF. The part of the circuit which is at rest, and if it is kept in uniform field, so we are assuming that the field is not changing. What is changing is the flux due to the motion part. So whenever there is an induction in the moving system, the induced EMF only belongs to that part of system which is in motion. And that is the proof that the rest part of the circuit, if it is not in motion, cannot have the induced EMF. So the motional EMF creates a localized EMF. Localized means what? It is confined between the two ends. So this entire rod we can represent equivalently as a circuit, as a cell. And this cell will have the positive polarity upward and negative downward. As you can see, negative is here and positive is here, right? So this cell, this rod which is translating in the field, we can replace by, you can see here, the rod we can replace by a cell of EMF value BVL. And the moment we do so, it is pretty easy for us to draw a circuit in which we can apply the rule of circuit as we have studied in the current and electricity. I hope this is clear.
Yes, sir.
So this is just one way of thinking. I'll show you some multiple ways of thinking. Just on it. So now this is the one way. So in a circuit, whenever you see a moving part, that moving part will create EMF. And such EMF we call localized EMF. Why localized? Because we can see clearly the polarity which is developed is localized. It is finitely separated, right? So we know that where is the positive and we know that where is the negative. So when we know exactly, it's a localized EMF. So in later part of this chapter, we will see that EMF can also be delocalized, and the net EMF developed in a circuit will be shared differently for different part of the loop. So we'll see the delocalized part later on. That will be the second concept of this chapter. Okay. The next part is when we have a circuit and the moving part is some, you can call it a slider or you can call it a thin rod. So let's say this is the slider which is sliding over the circuit. Let me complete the circuit. So we can attach some resistor here. And this entire arrangement is immersed in transverse magnetic field. So we can clearly see this is immersed in transverse magnetic field. Let's call it inform and transverse. Okay. Move it a bit here. Now, if I assume a moving rod, and let's call the length of the rod as capital L. And now we have something which we need to understand called the gauge length. So the gap between the rails, this is called the rails. And of course, let's call a rail. It is just like the train running on between on a rail, and the slider is sliding over the rail. Okay. Now you can see that when you design something like this, we call such circuit as pi circuit because of the symbol pi. We also write it like this, and this is the horizontal pi. We can turn like this. So all are same meaning. It's a pi circuit. So for that reason, they call it pi circuit. But of course, you can call it just circuit. That's good enough. So we have a length L, which is called the gauge length. What is gauge length? When we have a rod part of a circuit, the current will establish only in the loop. So definitely current will never pass through this part or this part, isn't it? Because that part is not part of the loop. Do you realize this? So when it comes to the circuit, the length of the rod which is actually put into use is the length of the rod which is part of the loop. Anything beyond is useless, and therefore this L will have no meaning, only this L will have meaning, and that's why we call it gauge length. So we use the word gauge length as the separation between the rail and between the points which is touched by the rod. Is this clear? Hello, hello. Is this clear?
Sir, are you able to hear me?
Yes, I can hear you now. Are you able to hear me?
Yes, sir, I'm able to hear you. Because he replied yes, sir, but
Okay, yeah, no problem. So now when we have a circuit, the polarity that we had shown earlier, that some plus will be here, some minus will be here. Now the same plus minus, this will not be at the bottom or top, it will be only near the junction where the loop is cutting the or intersecting the rails.
sir,
And
why so?
yes, because the loop will have a junction. This is called junction. And at a junction, the incoming current must be turned like this. So
Yes,
it is like I'll create some sort of charge accumulation here, so that when the current is coming like this, it is bent like this. So near every junction, some charge will accumulate to make the turning possible. Because at the end of the day, it is a physical particle called electron which has to move in a path, right?
okay, so the charge accumulation is used to turn its direction.
Yeah. So in a circuit, whenever there is a turn, it will create some charge accumulation to make it possible that it can go in the desired direction. Okay? And this is all done by the circuit itself. No need to worry that you are not supposed to think much about it. Circuit will take care of all such phenomena. Okay.
Yes,
Otherwise, how electron will come to know that it has to turn like this way or that way?
yes,
Okay. So whenever, let's say, if we have a circuit like this, and this is the root, and if some current is coming here, so as per the Kirchhoff's current law, some will divide like this, some will go like this.
yes,
So what will happen is that near this surface we will have some negative charge, and this negative charge will attract some of the positive. I mean, let's say if current is like a positive value, so this is attracted, and because of inertia, something will go here, and because of some inertia, to go like this. So we may have some charge accumulation here also, quite possible. And at this junction, the inertia will let it divide into two parts, like this. Understood?
yes,
So imagine if it is a path, if the other path, if the vertical path is having the lesser resistance, then the field will be so strong that it will push most of the charge from there, and very less amount will go from the straight path. So a path with no resistance will have the maximum. You can see it will let maximum charge to go through that path. Anyway, so the idea is the charge accumulation will take place only at the junction, and the part which is not a, and the length of the rod which is not part of the circuit, because this part is not as part of circuit, right? This will never participate in the current flow, isn't it? Do you realize this?
yes, sir.
And therefore, so anyway, so we only concerned about the gauge length. That is the first thing first. The other thing is, which we are actually talking about, let me make it a broader to understand it better. So let's say the rod is moving with velocity v, but because as the rod will go like this, we know some current will be established in this sense, because the inward flux will increase. So the to compensate as per the Lenz's law, the induced current will be like this, isn't it?
Yes,
Do you realize this?
yes,
So we can say as the current will go this way, the electron will go in the opposite direction, isn't it?
yes,
So if I consider an electron just for demonstration, and if I draw the FBD of the electron, I can say the electron will have two velocity, one towards right, which is the physical velocity of the rod. The other is the velocity that we know from the concept of current and electricity called the drift velocity. And the drift velocity is due to the field which is already present there. So the electron is not moving along the conductor, it is moving actually at some angle which is neither right nor down, it is at something in between, isn't it?
yes, sir.
So I can call this as v dash. So I can relate the drift as well as the v in terms of theta. So we can say v dash cos theta is the velocity of the rod, but v dash sine theta is the drift velocity. I hope this is clear so far.
Yes, sir.
So now what will happen is, as the rod will progress further, the electron will progress like this.
Yes, sir.
You can see electron is not moving straight along the rod, electron moving at some angle, and when the rod has translated towards right, the electron is here.
Okay.
Now the magnetic force, as we know it is a formula, the magnetic force, how we write? So we know the magnetic force is Q into V cross B. So in our case, it will be minus E into V dash cross B. And if I take the modulus, if I just write the magnitude, I can say E V dash B, isn't it? That's very simple.
Yes, sir.
Because even the electron is going at some angle, the magnetic field is still perpendicular.
Yes,
But what will happen is the net force, if I try to draw the direction of net force, the net force on the electron will be acting at V cross B. If you apply the V dash cross B, this is the direction of V dash cross B.
yes,
V dash cross B, but electron is negative, so the net force is like this.
yes, sir.
So force on electron will be like this. This is the, I'll extend this line. This is the force on electron. And this is equals to Q V dash B. Now, do you realize this part?
Yes, sir.
And you can clearly see that the force and the displacement are mutually perpendicular. So the total work done by the electric field on the charge is 0. Total work done by electric field on the charge is 0. So magnetic field cannot do work. Okay. Magnetic field cannot do
Yes.
work. Then the question is, who is doing the work?
Sir, partly the electric field and partly due to our motion.
No. The
Oh,
work is only done by the external agent. See, someone is moving the rod with constant speed, right? V.
the electric field is induced due to that.
Yeah, the work is always accomplished by some external agent. See, system cannot do work on their own. We need some sort of source of energy. Now, in
Yes,
case of current and electricity, the battery was there to do some work. Now we don't have any battery. We don't have some energy source which is directly connected. Okay. What you need to realize that if I draw the ABD of rod, which you can clearly understand, and let me draw the next part. If I draw the ABD, okay, of course we'll draw for the rod. ABD. So let me draw the electron first. This was the electron, and this was the net velocity V dash. This was the angle theta, and this was the magnetic force, right?
yes, sir.
E V dash B. And I'm saying that the rod is moving with constant velocity V. Let's say this is constant. Technically, the electron, if the electron will have the force, if you look at the force on the electron, it will have two components. E V dash B sine theta, correct? And other force will be E V dash B cos theta. Do you realize this?
Yes, sir.
But electron is not accelerating, isn't it? So the net horizontal acceleration must be zero, no?
Yes.
So how that is going to be zero? So the wall of the conductor, this is the force experienced by this is the reaction force, Fr. Reaction force due to wall of conductor. And that is why the electron is moving like this. Understood?
Yes.
So the reaction, and if I draw the ABD for the rod, because the reaction on the electron is right, so the reaction on the rod will be left. Okay, so some agent must be applying force to move it with constant velocity, isn't it? Do you realize this?
Yes, sir.
Okay, so numerically, it is fortunate that numerically the Fr is equals to EV dash. No. That is the force on one electron, right? This is the force. So this is the this is the reaction force due to wall of conductor. So this is the reaction force due to one electron on the rod. Okay. So a single electron is capable of creating this much force on the rod. So
EVD.
let's call by small symbol, small f, because I want to write for small f is for one electron, and then we have to analyze for the all electron in the part of the rod, right? So numerically we can say for each electron, the reaction force is EV dash B sine theta, right?
Yes.
And what is EB? What is V dash sine theta? Do you realize this? What is V dash sine theta?
VDC.
It is the drift velocity. So we can write as EB VD. So if I consider a part of the rod if I consider a small part of the rod of length dl and cross-sectional area A, how many electrons will be in this volume? Do we know the number of electrons in this small volume? So we have something called concentration N. So if I choose N as the charge carrier concentration, as we did in the current and electricity,
Here then NETL will be the
correct?
amount of number of electrons.
Yeah. So we can say the total number of electron will be NADL,
Yes, sir.
and therefore the DF, the net reaction force on the rod will be how much? It will be the Dn into force due to each electron, correct? If one electron is creating this much reaction, so the entire electron in the bulk will create how much reaction force? You can see it,
Yes,
right?
sir. Yes, sir.
Which is NADL, and FR we got as EBVD. And if you rearrange, you can clearly see the net force that the rod will experience, the DL length of the rod, force experienced by DL length of rod equals to, I'll just call DF. It is, you can see if you rearrange, it is NEAVD. We can rearrange, separate, and then we are left with DLV, right?
Yes,
And
sir.
by definition, NEAVD we call current. It is very fortunate that the answer is very much similar to the magnetic force formula ILV.
Yes, sir.
And we have derived from the very basic, just like we took one electron at a time and then we analyze. And from the laws of motion, we are coming to the conclusion that ILV is not the magnetic force on charge, rather it is the force on the rod.
Yes,
And it is not the force on the rod, it is like the reaction force. Numerically, they are equal. And therefore, if you take that part of the rod and if you try to draw the ABD, the external agent must apply this much force to move it constantly, right?
yes, sir.
So who is doing the work? It is the external force. Fext into dx is the work done, and that is supplying energy to the system. So what we don't see, the visibly, the agent is not shown to us, but when we have some event happening, the agent must be present. It is that agent which is creating the, it is that agent which is creating the force on the rod. Understood?
Yes, sir.
So if someone will ask you that in a electromagnetic chapter, when we have a circuit without a cell, and if they ask you who does the work, we must understand that without cell, the electric field is not present which can do the work, and the induced field part of the same circuit, so internal field never do the work, and therefore it is the external force which we don't see directly is responsible for doing the work and hence supplying the energy to the system. Understood?
Yes, sir.
So that is the basis of electromagnetic induction. So we can say the net force will be here ILV. I can just integrate, assuming everything is as per the situation. And now you can see the L will be actually, the L will be the part of the rod in which current is flowing, right?
Yes, sir.
Because only the moving part, the part of the rod in which the electron is in motion will create that force. Now the part of the rod in which the electron is not in motion will never create the force, isn't it?
Yes, sir.
So even in the ILB formula, we take the gauge length, we never take the actual length of rod. Is this clear?
Yes, sir.
So we need to remember certain thing that in case of magnetic circuit, the magnetic field, as we know, cannot do the work. The energy in the system must be derived from some external source. Is this clear?
Yes, sir.
So far, we are keeping the discussion for the uniform and transverse field. We'll soon try to generalize it for any field and any direction. Now, still we haven't discussed the induced EMF part. So, induced EMF is basically internal work done upon charge. Okay. Now you can see the electric field. Now you can see something here. What is the component of magnetic field acting downward?
Cos theta.
So
I mean,
it is,
okay, that's a force.
yeah.
It's, sir, downward there will be no component of
This
magnetic
will happen.
field.
This is the net field, no?
Sir, it's a net force.
Yeah. So this is the net force on the electrons. What is the component downward?
Sir, AV dash B cos theta.
Yeah, it is EV dash B cos theta, right?
Yes, sir.
Let's call E F parallel. So A parallel is FM cos theta, right?
Yes, sir.
So we can say work equals to F parallel into length of the rod, and the charge which are moving is, let's say, 1 electron. So if you are moving charge electron from the top to bottom, this is the equivalent of induced EMF, isn't it?
Yes, sir.
And that will be equals to how much? Let's calculate. F parallel is E V dash B cos theta L upon E. E gets cancelled, so you can see clearly it is V dash cos theta into BL. And if you remember, the V dash cos theta is nothing but
V.
It is a V. So answer is again BVL or BL.
Okay, sir.
So no matter whether we have isolated rod or a rod which is part of some electrical circuit. So no matter whether we have an isolated rod or a rod which is part of some electrical circuit, the formula remains same, and as this is proved. Okay.
Yes, sir.
Now we will go for the final derivation of motional EMF. All are formula of motional EMF, but we saw something more deeper, that the force on the rod is also ILB. Okay, that we could have derived directly, but I just try to show you the very scratch that how all formula come into picture. You can devote some time to understand and try to analyze all these things on your own till you have some level of comfort.
Sir,
Then, yeah.
sir, in the FDD, didn't we like take the electric field?
No, you can see I haven't shown anywhere electric field, right?
Yes, sir.
So it is the only magnetic field which is sufficient to explain, right?
Yes, sir. Sir, but why haven't we like taken that?
Yeah, it is all about the way we understand that. See, because the rod is kept in the you can say which field? The rod is kept in the uniform
Magnetic.
and external. The field is external. The external field given to the system is B, right?
Yes, sir.
Now the other field is not present, and that will be induced, but we are not trying to show the induced part because that is the internal process. Okay.
So FBT only shows the external forces that.
No, you can think this way. You can think this way. If the electron is going downward, it means the field is upward. So induced field is upward, right?
Yes, sir.
Because the electron is moving with constant velocity, so you can think this way: the electric force is balanced by the A parallel.
Yes, sir.
It's the same thing. Okay. So you can say the upward electric force is equals to downward parallel component of the magnetic field, isn't it?
Yes, sir.
And you can again show that the electric force into L is the work done upon charge. And F electric is how much? So we got the answer as F parallel L by E, and therefore it is eventually same formula.
Yes.
Understood?
Yes, sir.
There are various ways of interpretation. What we need to remember is BLV, no matter what. And in BLV relation, everything is mutually perpendicular to each other. So B must be normal to L. Okay. The V must be normal to L. And if they are not mutually perpendicular, we take a component and we write the formula BLV. So in your brain, only store only one formula, BLV. Which B? The B must be normal to the L. Which V? The V must be normal to the again L. Okay.
Yes, sir.
Now comes the vector notation. So vector form of writing emotional. Now this can be tricky, but it's easy to just remember. If a rod is moving in transverse field, so B is present. Okay. And the rod is, let's say, moving with velocity V. Now, in case of isolated system, there is no current, right? So the electrons are all are rest only. Because the time taken to accumulate the plus and minus is almost 0 second. It's like a nanosecond. So now, if the electron is at rest, what we can say, the net Lorentz force on this must be 0. See, I have no idea how the field is, but even if any isolated rod is moving in a circuit, what you can always write is the Lorentz force must be 0. At equilibrium.
Yes.
So we are writing for electron, right? And the Lorentz force is sum of electric force and magnetic force. And the electric force we can write as minus E into the induced electric field. Of course, the E will be induced only. Correct?
Yes.
And this E will be something like this. Even the E is having different direction. What we are concerned is the E along the length. I just want this component of E. But luckily here we have E here. Okay. And the magnetic force is what? Q into V cross B. And we can say the V is same as that of the rod, isn't it?
Yes.
And if this is 0, you can clearly see the E turns out to be minus V cross B. Minus V cross B. Understood?
Yes.
And that is why the induced EMF, we can go by the definition of potential. So the motional EMF is by definition is minus E dot dl, if you remember the formula from electrostatics.
Yes.
But E itself is minus V cross B dot dl. And so the formula becomes V cross B. This is the vector notation of writing. And of course, it's a scalar at the end because we know that potential is scalar. So we have dot product at the end. So V cross B is a vector. But once you take the dot, it becomes a scalar, right?
Yes.
So we can see something clearly here. The motional EMF is V cross B dot dl. And therefore, we can again derive multiple things from here. So when you come across a generic problem in this chapter, although I'm saying that 98% problem which you will face even in JEE advanced to normal examination of Olympiad, only knowing the VBL is sufficient to solve any question. It's not difficult. VBL is more than sufficient. For some situation, we need to know the vector formula. So some interesting properties of this formula, which we'll try to explore. So the first thing first, if B is uniform over the length of rod and rod is in pure translation. Now, what do you mean by pure translation?
It's
The
1, 2,
V,
3.
the V is same for all points, right?
Yes.
Because if it is in rotation, then V cannot be same.
Yes.
So every point will have different V, isn't it?
Yes.
So we'll see that situation also separately. So in such case, we can rewrite the above formula as V is constant, B is constant. So take it out. The dot will be there, and then dl vector will be inside. So what is the integration of dl vector? It is the displacement.
Sir, the small
Isn't
n.
it?
Yes.
It's a, yeah. So let me talk about L first. The L cannot have the direction. I mean, of course, L is not a vector. L is simply some length of. It is simply some dl is the length of some part of the rod. But L vector gets the sense from the sense of induced EMF or sense of induced current. So let's say if you know the V cross B direction is upwards, you can take upward as the dl positive value or direction of dl also. So about L vector, imagine if you have a rod of some random shape, but one thing is clear that it is translating. And moving in this direction. So what L represents? So if you look at the beginning of this, the segment and the end of the segment, because if you add multiple dl vector, if you add this DL with this DL. We know from the vector triangle law, this will be the resultant, right? This is the net value.
Yes, sir.
If you keep on adding next DL, the DL, the final, the resultant vector will be like this. So eventually, when you come to the end point, this is the displacement of the final vector or the resultant vector, right?
Yes, sir.
So L is only the line joining the beginning of the segment to the end of the segment. It has nothing to do with the shape. The shape really doesn't matter if it is in uniform and transverse magnetic field.
Yes.
So for uniform and transverse magnetic field, the L is pretty easy to understand. It's only the end to end. The shape doesn't matter. What matters is the beginning and the end.
Yes.
So if we have a rod, so this again condition is peculiar condition. If we have a rod in which the V itself is parallel to the length of the rod, and if the magnetic field is, let's say, transverse, so V cross B will be upward. So definitely the DL vector and the DL is going to be like this, right? Along the length.
Yes, sir. Yes, sir.
So the V cross B and the DL direction cannot be parallel. It will be mutually perpendicular, right?
Yes, sir.
And therefore the dot between them will be 0. So elementary motional EMF will be V cross B dot DL, and you can see clearly this is 0. Because the dot product of two vector is 0 if they are mutually perpendicular, right?
Yes.
The other way of thinking is the V cross B will try to move the charge in its direction, but it is not possible because the width of the rod is 0. No? It's a thin rod, so it means there is no gap actually. If I make it a flat plate, the V cross B can create the potential difference, right?
Yes, sir.
So for thin rod, what we need to remember that a V cross B cannot create any motional EMF because it will fail to separate the charge. We don't have the space between the separation, right? So even we try to separate, we won't be able to separate it, isn't it? Do you realize this?
Yes.
So this is a condition that we need to remember that for a situation when V cross B is perpendicular to the DL vector itself, there is no EMF induced.
Okay, sir. Sir, are you able to hear me?
Yes, yes, I can hear you.
Okay.
Okay. Next. So let's do some question based on the inform. And if you remember, we have done something like this previously in the magnetism also, right?
Yes.
So if the velocity is like this, so what we have to remember is only VLB or VBL, but the V must be normal to L and B is anyway transverse. The way of looking at it is, think about the B as the light rays, look at the shadow of the segment and replace the shadow by a line by joining the beginning and the end of the shadow, and then look at the velocity. Take the normal component of velocity and multiply all three together. VBL, that V, that L, that B. Okay, think this. So what will be the answer here? Emotional.
So 2a plus b sin theta.
Yeah, so 2a plus b into v sin theta, right?
Yes.
It's pretty easy. The only thing we need to remember is VBL. Now, which V, which B, and which L, you can always think. It's not that difficult. Okay.
Yes.
I mean, it is pointless to give you a lot of questions, but you can think anyway. There is one famous question. Just solve. So what will be the induced EMF in the moving part? What is the motional EMF? Assume the field to be transverse.
So BVL sin alpha plus sin beta.
It is not L, it's L1, L2. No?
Oh, yes, sir. L1 sin alpha plus L1 sin beta.
Correct. So the total length which is normal to the velocity is this much only. Okay. And then,
Yes.
so what we'll do is we'll solve some more problems in the next lecture. We'll see we'll keep the motional EMF as one separate topic to be discussed in detail. And we are going to solve a lot of variety of questions, more than 10 or 12. So the next lecture will be all about the motional EMF, and then we will start the circuit part. Okay.
Yes, sir.
All right.
Sir,
Bye and take care. Yes. Tell me.
sir, in current electricity, when like in the drift velocity concept, like when electrons are accelerated, they maintain the same velocity twice through an
See, first of all, you need to understand the difference between the localized motion and the bulk motion. So at local level, it is accelerating, but on a bulk level, it is not accelerated. So you can think like the marriage procession in which people are dancing. Okay.
Yes.
But if you look carefully, that the entire the Bharati, what we call, is moving at constant speed forward, right? But they do dance, they do make some random motion inside. But if you look at the entire crowd, it is moving constantly. That's the idea of drift and the individual motion. So individually they are accelerating. So one of the dancer is running back and forth. But is the Bharati moving with the same speed? The answer is
Yes.
no. The entire Bharati, if you look as a whole bulk motion, the bulk is constant, and drift is defined for the bulk, not for individual. Understood?
Yes, sir.
So the individual accession is of no use. So when we derive the formula, we try to make use of it. Any other doubt?
Sir, no other doubts.
I'll share the video links because it will take some time. So I will take some when I'm free. So I'll collect, and it will take at least 1 hour for me to search and send. So it's a tough
Okay,
job. That's why I always keep on saying, okay, whenever you have lecture, you just remind me immediately. I'll send you immediately. That's a good way. But anyway, I'll keep on sending.
sir, from now on, I'll remind before
Yeah.
the next class comes.
Like today, I will send you right now. Okay, so it will take some maybe 20 minutes. Then I'll send.
Okay, sir. Sir, because like you said that it will take time to download like the lecture video. So I
No,
was
no, no.
like,
What I'm doing is all of your lecture is now I'm putting on a YouTube channel, in my new channel, and I'll share the link. You can watch it there also. So for you, there is no need to go and see. So like I have put all the magnetism lecture there.
oh, okay, sir.
Yeah. So all of your magnetism lecture is there. I have already started putting the EMI lecture also. So I think from henceforward, all of your lecture will be there. So probably you can go and see your lecture. I mean, that's your lecture.
Yes. Sir.
Yeah.
Okay, sir.
I'll
Sir,
share the link.
is it like accessible to everyone?
No, it's like only with link. If I share the link, you can watch it.
Okay, sir.
Yeah. But it is public. Mostly it's public. People can watch it.
Yes. Oh,
Yeah.
okay, sir.
Don't worry, you will be famous only.
Sir, what if I made any silly mistake in the lecture and it comes?
No, even I make mistakes, so that's okay.
Okay, sir.
Yeah. No need to worry.
Yes.
Okay. Bye. Good night.
Bye, sir. Good night, sir. Thanks, sir.